Hello everyone and welcome back to my channel. Uh, Today I discuss about numericals on Norton's theorem. In the previous lecture I have discussed about different problems on superposition theorem and Thevenin's theorem. If you have any doubt regarding that, please let me know. Now in this video I'll discuss problems on Norton's theorem and maximum power transfer theorem. Okay, so let us begin. So this is the first problem. Determine the Norton equivalent circuits between terminals A and B for the circuit shown. Okay, so before going to the application of Norton's theorem, let me in very brief describe what is Norton's theorem. Okay, so Norton's theorem, in very simple language, if I say Norton's theorem in any linear bilateral network, a circuit can be converted to a current source in parallel with the internal resistance of the circuit. So the current source, the value of current source is named as ISC, that is the short circuit current, and the internal resistance is named as Norton's resistance also, which is same as the Thevenin's resistance, which was considered in Thevenin's theorem. Okay, so now the short circuit current ISC, that is nothing but the current flowing in the circuit when the load is removed and the open terminals of the circuit are directly shorted. When we directly short the load terminals, then whatever current is flowing through that branch, that current will be known as the short circuit current. Okay, short circuit current. And R Norton, Rn or RTH will be the equivalent resistance of the whole network as viewed from the open terminal. Okay, so as viewed from the open terminal, when we view from this side, okay, when we view from this side, then the resistance whatever is appearing in the circuit, that resistance is called the Norton circuit or Thevenin's circuit, Norton's resistance or Thevenin's resistance. Okay, so let us begin with the problem. Determine a Norton equivalent circuit. Okay, here it is asked to draw the Norton's equivalent circuit. Now whenever you are asked to draw Norton's equivalent circuit, your first motto will be to draw this circuit. Your first work will be to draw this circuit. Okay, where a resistance will be there, where a current source will be there, giving a current ISC. Okay, and the resistance, don't write the values, don't write these formulas, just draw a current source in parallel with the resistance. That is Norton's equivalent circuit. Draw the Norton's equivalent circuit. Okay, now the current flowing here, it will be named as ISC, I suffix SC, that is the short circuit current. Okay, and this resistance will be Rn, that is the Norton's resistance. Okay, or the Thevenin's resistance also you can see. Now how to find out ISC? Now your next work will be to find out ISC. How to find out ISC? See, here you may ask that there is no load connected, but it is not required, right? Because you are asked only to find out the equivalent resistance. For that, no load is required. So obviously it is between open terminal. The load should have been between open terminal, this terminal A and B, and it is removed. Okay, so we'll directly short this terminal A and B. We'll directly connect this terminal A and B. Okay, we'll directly short this. Now what will happen after shorting this? When we short this circuit is complete, so current will flow in this branch also. In the present circuit, in this circuit, there is no current flowing here because it is open circuited, right? Only current will flow here. But once it is short circuited, current will flow in this branch also. Now as it is short circuit, what is the meaning of short circuit? Short circuit means the resistance of this path is assumed to be negligible. Okay, the resistance of this path is assumed to be negligible, so it is short circuited. Now when it is short circuited, current will flow in the circuit, right? Current will flow, and at this point there are two branches, so that current will be divided into two, right? Some current will flow from here, some current will flow from here. Now it is the nature of current to always follow the least resistive path. Okay, it will always follow the least resistive path. In whichever branch less amount of resistance is there, current will always choose that path. Or you can say that wherever more resistance is there, current will be flowing. It is obvious, right? Resistance is what? It is opposition to current. Whenever opposition is high, less current will flow. When opposition is low, more current will flow, right? So when it is short circuited, that means what? There is no resistance, the resistance is negligible. So what will happen? In the other branch, no current will flow, right? All the current will flow through the short circuit path. Why? Because it will find here hindrance, it will find resistance here. Why will it follow this path? It will always follow this path where least resistance is there. So in the circuit, what will happen when we connect this will be short circuited. So current will flow here and this path will be nullified because all of current coming from here will be flowing here. So it will behave like open circuit. No current will flow through this branch. Okay. Remember that current always flow through the least resistive path. Since this is the least resistive path for the current, whichever is the short circuit branch one. So all of current will flow through this and this resistance will be negligible, right? This resistance will be neglected, or we can say this part is open circuited. So what will happen? A short placed across terminals A and B will short out R2 as well, right? It will short out R2 as well. This will be nullified. Hence ISC, that is your short circuit current, will be what? So in the circuit, what will remain? Only this short circuit will be there, this resistance will be there, and this voltage source will be there, right? So what is the current flowing? Here there is no resistance. Here this is R1 resistance. So what is the current? It is V by R. So it is E by R1. So short circuit current flowing will be E by R1. Okay. Now move on to Norton's equivalent resistance. Again, as I have told you, Norton's equivalent resistance and Thevenin's resistance are the same thing. Okay, just different names because they are applied in two different theorems. Hence the name, but method of finding the resistance is same. Okay, so again for finding out the Norton's equivalent resistance, we'll remove this voltage source and replace it by the internal resistance. Since there is no internal resistance, this will be directly shorted, right? It will be directly shorted, and we will find that this R1 and R2, they are connected in parallel. Okay, R1 and R2 are connected in parallel, and that will give you the Norton's equivalent resistance because no other resistances are there in the circuit. Only R1 and R2 are there. So this Norton's resistance will be equal to R1 parallel to R2. Okay. So ISC is given by E by R1. That is not the formula. Okay. It is just that for this circuit we are getting ISC as E by R1. ISC is E by R1 and resistance is given by R1 parallel to R2. Okay. This is a very simple problem just to describe Norton's theorem and just to give an idea how Norton's theorem is applied in solving a circuit. Okay. Next I'll move on to another problem. See here what will happen. Using Norton's theorem, find the constant current equivalent of the circuit shown. That means we need to find out the current. Okay. Constant current equivalent of the circuit. Again equivalent circuit will be found out. So what is the first step? First step is always to remove the load. Now here is no load again, this terminal is open, right? Then we'll short the open terminals. So we'll directly short this terminal. Okay, we'll directly short this terminal. What will happen then? If you directly short, this circuit is completed, right? So resistance will flow. Now see, in the previous problem, there was no resistance in this whole branch. When this is shorted, here there is no resistance, here there is no resistance, and this short, when we will short it, there will be negligible resistance. So there is no resistance in this complete branch, right, in the previous problem. But in this problem, see, even if we short this branch, this 15 ohm is there, so there will be resistance in the branch, right? There will be resistance because this resistance is there, but in the previous problem there was no resistance, just keep in mind. So if we, even if we short this, we are just shorting these two terminal, that means there will be no resistance in this particular terminal, between these particular terminals, okay. But here in this complete branch there will be resistance 15 ohm, okay, fine. Now we are shorting it, okay. What will happen when we short it? Again we need to find out the ISC, we need to find out ISC, right? For that we need to find out I. So this 15 ohm and this 10 ohm, they are connected in parallel. The equivalent is connected in series with this, right? So these two are in parallel, then in series with this. So it will be 10 plus 15 into 10 divided by 15 plus 10, that is the equivalent of 15 and 10, okay. Since these two are parallel, r1 r2 divided by r1 plus r2, that formula is used, 15 into 10 divided by 15 plus 10. So after calculating, we will get 16 ohm as the total resistance of this network. For this network, the total resistance is coming as 16 ohm. Now total resistance is 16 ohm, current voltage is 100 volt, so current flowing will be 100 by 16. So battery which is giving a current of I, that I will be is equal to 100 by 16, so it is coming as 6.25. so this is this current and not this current. Our aim is to find out ISC, okay. Our aim is to find out ISC. So for finding out ISC, we'll divide this current by using current divider rule. So this ISC will be equal to what? Opposite to the total current. Total current I, that is 6.25, into opposite resistance. Opposite resistance is 10 ohm. So in this current I into 10 ohm divided by the total resistance 15 plus 10, that is 25. So here it is, see, 6.25 into 10 by 25. 10 divided by total current resistance is 25, so it is 10 by 25. So current through AB is equal to ISC is equal to 6.25 into 10 by 25. So our first aim is fulfilled, to find out the value of this current source, that is 2.5 ampere. Next, our next aim is to find out the equivalent resistance, right? So for finding out the equivalent resistance, what we do, we will remove all the sources from this circuit. Will remove all the sources. So this source is removed. See, R is equal to 0, that means what? The internal resistance is negligible, right? So there is no resistance, only this. If we remove this, only this 10 ohm will remain. So 10 in parallel with this 10, then in series with this 15, right? This 10 and this 10 are in parallel, and the equivalent is in series with 15. So 10 and 10 in parallel, in series 15. So equivalent resistance is 20 ohm, that means RTH is coming as 20 ohm. So our Thevenin's equivalent network becomes ISC in parallel with RTH, where RTH is coming as 20 ohm and the voltage is the current is coming as 2.5 ampere, okay. So I hope with these two examples, Norton's theorem is clear. Solve more problems related to Norton's theorem and the other theorems whichever I have discussed in the last video. Try to solve more and more problems, then you will understand the difficulties which you are facing, and again you will understand which method you need to apply. If the name of the theorem or name of the method is not mentioned in the problem, then which method will be convenient convenient for you to solve, that you can decide. And then this is only possible if you solve more and more numericals, okay. Now I move to next theorem or a new application of next theorem, that is maximum power transfer theorem. So again I will brief about maximum power transfer theorem. Maximum power transfer theorem says that the load resistance will abstract maximum power from the circuit when the load resistance becomes equal to the equivalent resistance of the network. Okay, so in short we can say that the load resistance RL will abstract maximum power. Okay, it will abstract maximum power only if that RL becomes equal to RTH, because RTH is nothing but it is the internal resistance of the circuit. Okay, or equivalent resistance of the circuit. So when this equivalent resistance of circuit becomes equal to the load resistance, then only the load will abstract maximum power. Okay, that is maximum power transfer theorem. Next, we'll take this problem now. In the network shown in figure, find the value of RL such that maximum possible power will be transferred to RL. Okay, maximum possible power will be transferred to RL. So this is the first problem. Find the value of RL. So you need to find out the value of RL. Now it is mentioned that maximum power is transferred to RL. So if maximum power is transferred to RL, that means it is clear that RL is abstracting maximum power, right? So the condition will be RL is equal to RTH will be applicable, because RL is abstracting maximum power, right? So RL will be equal to RTH. So in order to find out RL, you will have to find out RTH. Now that RTH will be equal to RL. Okay. So to find out the value of RL, we will find RTH. Now for finding out RTH, we'll have to remove RL from the circuit. RTH is again the same RTH which I talked about in Thevenin's theorem. Okay, so for RTH this will be removed, RL will be removed. So once this and RL is removed, these 3 and 3 are in parallel and in series with this 2 and 1. So as seen from the figure, from again viewed from the open terminal. Okay, so 3 and 3 are in parallel in series with 2 and this 1. So this will give you 4.5 ohm as the total resistance or Thevenin's resistance RTH. Now since it is abstracting maximum power, that RTH will be equal to RL. So we have calculated the value of RL. So our first objective is fulfilled. Next, find also the value of the maximum power. So what is maximum power? Maximum power drawn by RL will be is equal to, it is, we can say it is V square by R, right? What is the formula for power? It is V square by R. Again, V is what? V is in maximum power transfer theorem, V will be equal to the VTH. Okay, so VTH first, then our next another work increases, which is to find out the value of VTH. So VTH is the voltage appearing across this, right? All right, voltage appearing across this. So VTH equals the drop across the vertical resistor 3, because no current flows, right? No current is flowing here. So whatever drop is occurring here will be occurring here as well, right? So since 15 volt drop occurs, two series resistances 3 and 3, so current will be 15 by VTH will be equal to what? Apply voltage divider rule, it will be equally divided. So it will be 15 by 2. So 7 by 5 and 7 by 5. Okay. Now So it is v square by rl. Then we can find out by using the formula, and we get the value as 3.125. What is our next? Power supplied by source under this condition. Power supplied by source under this condition. Since same power is developed in RTH, power supplied by source is equal to 2 into this. Whatever power is supplied to RTH, same power is transferred to RL as well. So it will, the total power will be equal to this into 2. It will be simply multiplied by 2. So it will be 2 into 3.125. Okay. So this was the application of maximum power transfer theorem. Since this basics of RL, basics of RTH and VOC, all these things were discussed in Norton's theorem as well as Thevenin's theorem. So I have taken a very small problem on this, and since RTH and VTH, all these things are known to you, and how to calculate these values are also known to you. So I have discussed only one problem here for maximum power transfer theorem, and this is how we apply maximum power transfer theorem in solving a numerical. So with this I am finishing the first module. Only one topic is left, that is the some numericals on star delta transformation, that I will discuss in the next video. uh, so if you have any query, you can ask me. In the next video I'll discuss a few numerical on star delta transformation, and we'll move to the next module. Thank you for your time, and you have any query, please ask me. Thank you very much.